So this is supposed to be the end of my series of talks here, so I guess for some people it might be a bit sketchy, and for others it might be a bit repetitive, but I apologize, but I'll try and make it as self-contained as possible. So let me tell you the basic problem that I'm interested in as soon as I find the right page. Okay, so let's suppose G is a simple Lie algebra, finite dimensional over the complex numbers. Then it's well known that there's an infinite dimensional algebra called the affine Kac-Moody algebra associated to it. Which is associated to it very canonically. And it has a nice construction. So it's constructed as follows. So you first form the loop algebra. And this is just, you take G tensor CTT inverse. So it's the space of Laurent polynomial maps from C star to G. And you define a bracket structure, so commutator. In a very simple-minded way, you take an element X tensor F and Y tensor G, and the commutator is just X bracket Y tensor FG. Okay? So one definition of the Kac-Moody algebra, affine Kac-Moody algebra, is that G hat, the affine Kac-Moody algebra, is a one-dimensional, so is the universal central extension of LG. So that means we have a non-split short exact sequence, and the center is actually one-dimensional. So we have 0 to CC to G hat to LG to 0, non-split. Okay. So, so I'm not going to tell you exactly how this is defined for the following reason. What I'm really interested in is a category of finite dimensional representations of LG. So of LG. So this is my interest. Okay. And the reason we're not going to worry about the center is it's a very simple lemma that of the loop algebra or G hat. So let's say G hat to begin with. Yeah. And the simple lemma that you can prove is that the center acts trivially, the center of G hat acts trivially on LG. Okay. On finite dimensional representations of LG. So I'll forget all about my center and only focus on finite dimensional representations of the loop algebra. Okay, so of G hat, so now we know that it's the same as the finite dimensional representations of LG. So there are a number of reasons you could be interested in this, and also their quantum analogs. They show up in various kinds of integrable systems and lattice models and so on. But actually, they're just intrinsically interesting for the following reason. So this is interesting. So for today, it's just interesting for the following reason. It's a non-semi-simple category. Okay. So that means there are extensions in this category, and what I'm interested in these days is to understand its homological properties. So let's first construct examples of representations. So there's an ultimately cheap way to construct examples of representations of LG. So if you take any non-zero complex number, you can take the evaluation map, and you just evaluate your polynomial at what? A. Right? Then you can take any representation of it, of G. You pull it back, and you have a representation of LG. So rho composed with FA from LG to NV is a representation. And clearly it's irreducible, implies irreducible G module implies that V is an irreducible LG module. So this is very cheap. These are not all the irreducible representations. To get any irreducible representation, you just have to work a little bit more. So any irreducible representation is just obtained by taking a tensor product at distinct points. So you give yourself k distinct points, give yourself k irreducible representations. So let's call this F star. So let me call this F star. Vk is by taking such a tensor product where A1 up to Ak are distinct, and the Vi is irreducible. Okay. This is an old result. Sorry?
So first statement is irreducible as a G module implies irreducible
as an LG module, yes.
And that's not obvious.
Oh, it's trivial, right?
Why is it trivial? Oh, that's subjective.
Okay. So the fact that this is irreducible is also not very hard to do. You have to work a bit more to show that these are all the irreducibles. Okay. So let's now look at, so if our category was finite dimensional, I'd be out of a job by now because we'd have understood the entire category. So let's look at extensions in this category. So extensions. Okay. So let's take two irreducible modules. So I haven't introduced all the endless notation, but so let P plus be the weight lattice of G. So we'll have assumed now that we've fixed H contained in G, a Cartan subalgebra. We'll have a set of roots. Pi will be the simple system, and so on. Okay. Q, root lattice. Okay. So let me take an irreducible representation. Actually, yeah. So let's supposing that V is an irreducible representation of G, V and W. And let's assume that there's the space of G module maps is non-zero. Okay? So there are plenty of such examples. And so now I can construct an extension. So let's set U to be V direct sum W. This is, of course, a G module, so as G modules. And I'll define a GT module structure, LG module structure on it. So if you take X tensor F and you take a pair VW, so in the first factor, you can, and let's fix A and C star. So in the first factor, you make it act as evaluation. And in the second factor, continue to make it act as an evaluation, but now you give yourself a correction term, and the correction term is the first derivative. And phi of x tensor v. So I haven't picked phi. And so let me pick a non-zero element phi over here. Okay. So if you look at this, it's quite clear. So if v was 0, then this is quite clearly a submodule. Right? So it's quite clear that we have 0 to w to u to v to 0, short exact sequence. And for instance, if v and w are non-isomorphic, it's obvious that this is non-split because I'm clearly going in over here. Right? So and even otherwise, it's quite clear. So this is non-split. So in fact, one can prove the result that so in fact, you can compute x1 between irreducible representations and actually prove that x1 vw is isomorphic to these G module maps. And this is G here. Okay, so there are extensions, and so obviously one should look into more detail in the homological properties, as I said.
There's no other way of saying that the right side is an LG module.
This is not an LG module.
No, the left side is.
No, X1 LG. So, okay, so I've been trying to understand these things, and so how does one understand? One copies. So you look for examples in representation theory of non-semi-simple categories. Of non-semi-simple categories, and you see how much of their ideas you can steal or make to work in this context. So there are two well-known categories. One is the Bernstein-Gelfand category O. Right? So such examples of such categories which are known and extensively studied. So the BGG category O for a simple Lie algebra. So what is the BGG category? So it consists of modules M, G modules M, which have a weight space decomposition. So that means you can write it as a direct sum of eigenspaces for the, yeah.
Instead, you can actually write E and W as Q at the same point. Q A star.
Oh, yes, right. So it's X1 LG, F1 star, F A star V, comma, F A star W. And otherwise it's 0.
Same evaluation.
It has to be the same evaluation, otherwise it will be 0. Yeah. Okay, so this is the BGG category. So it consists of G modules, which are weight modules. You demand that dimension of M mu is finite. It has to be locally, so its M is UN plus locally finite. So this is the positive part of your Borel, locally finite. And that's it. Those are the only three conditions that you need for the BGG category O. Okay? That doesn't follow. Yeah, I guess that doesn't follow, does it? Yeah. That's all. I thought you only needed that in the. No, I don't think you need that. I need M to be finitely generated. Once I have that Kac-Moody's condition is that, but finitely generated you don't. Yeah. So n plus is, of course, the sum of the positive root spaces in G. And un plus locally finite means if you take any element in M and you look at the n plus module through it, it's finite dimensional. Okay, so for all M in M, the subspace un plus on M is finite dimensional. Okay, so this category has three. So associated with any element mu in H star, there are three important modules associated to to mu. One is the so-called Verma module. The next one is its irreducible quotient. So the Verma modules are denoted m lambda. The irreducible quotients are denoted v lambda. And then their projective covers, which are denoted by p lambda. Sorry, lambda instead. Thank you. Okay. So what is known and relatively easy to prove is that the irreducible objects in O are precisely, so the irreducible objects in O are precisely v lambda. And you also have this following, what's it called, a series of surjections. So p lambda maps onto m lambda, which maps onto v lambda. Okay. And it's perfectly possible for all three to be the same. Okay. Okay. So what Bernstein-Gelfand and Gelfand did was to relate these three modules in some very nice way, which really led to the theory of all these Kazan-Lustig polynomials and so on. So BGG's result can be formulated as follows. So p lambda, one can prove, has a filtration so p lambda contained in p1 contained in p2. We're still in the finite dimensional case, yeah. I'm just describing the classical BGG result. So they showed that there was a filtration such that the successive quotient pi by pi plus 1 is isomorphic to m of mu I for some I. Mu I. Okay? So every quotient is a Verma module. It's also known that objects in the category O have finite length. So you can talk of the Jordan-Holder series. So m lambda has a Jordan-Holder series as well. Okay. So the BGG results, what the BGG result does is to relate these filtration multiplicities of the Verma modules to the Jordan-Holder series of the filtration multiplicities of the Verma modules in the projectives to the filtration multiplicities of the irreducibles in the Verma. So it's easier to write. So p lambda to m mu. So the number of times m mu occurs in that filtration is equal to the number of times v mu occurs in m lambda. Yeah. That comes out of this, because you know that the Jordan-Holder series is given by the dot action. Yeah. Okay. So it's non-zero exactly when it's a dot action. M mu v lambda. Yeah. I thought I changed it. Yeah. Okay. So in particular also that so if you had any filtration where the successive quotients are wild modules, it's independent. The number of times anything occurs is independent of the choice. So what is the point of proving such a result? So M mu has a very simple character. So the Verma module's character can be easily computed. Okay. So by the character, I mean this function. So the character of M in our category O is a function from H star to Z plus, which will send mu to the dimension of M mu. Okay. So this the Verma module's character can be very easily computed. The character of the irreducible is very hard, and so is the character of the projective. So what this theorem does is to somehow interpolate something simple between the two characters. And so this theorem really sparked a lot of development in the entire study of the category O really began with this. So this is one category. This is one category which is of interest. And let me just make one more comment. So as somebody already noted, the role of the the role of the center, so the role of ZG, which is the center of the universal enveloping algebra, plays a very important role, is crucial. Right? Harishchandra's theorem that the center is a polynomial algebra in variables is critical in the study of this category. And here's our sort of first problem. The center of the universal enveloping algebra of LG, on the other hand, is trivial. It's just the complex numbers. So this already is sort of annoying, to say the least. Okay, so then there's another example. So because I didn't know what to do with the center, you continue to look for examples. So the other example, which is representations in characteristic P. So modular representation theory. So this is, again, so the representations here are not, so the category of representations are not semi-simple. Okay. And so to understand this, for instance, there's all this work of Klein, Partial, and Scott, or Donkin, and so on. So Klein, Partial, and Scott introduced and studied the notion of highest weight categories. Okay. And the point about this is they introduced an abstract formalism, and then they could derive all kinds of homological properties just from the fact that you had a highest weight category. So so what was the highest weight category? I won't go into the entire definition, but I'll just make the point. So for a highest weight category, so let's call that C, what you need is a poset lambda, partially ordered poset. It has to be what's called interval finite. That means if you take any 2 points in this poset, there are only finitely many things between them. Okay. For each element in lambda, you have 3 objects. So the role of the Verma module is played by what is called the standard module, which I'll denote delta lambda. The role of the simple is the same, so I'll continue to call that V lambda. And then you have your projective cover. And again, you have the same maps. Okay? And you need one more thing. You don't need something quite as strong as BGG, but you need that P lambda has a filtration by delta mu's. Okay, so you replace the Verma modules by the standard modules. And if you look at the multiplicity with which a delta mu occurs in P lambda, then that's non-zero only if I think mu is less than lambda. Or is it bigger than lambda? One. I think it's bigger. Okay. So if you have a category in which you have all these things, then it's called a highest weight category. And then it's if lambda is a finite poset, then it's Morita equivalent. So if lambda is finite, then C is Morita equivalent to the category of representations of a finite dimensional associative algebra. Quasi-hereditary, what they call quasi-hereditary finite dimensional associative algebra. And there's lots of stuff done by this by people like Ringel and so on, and so you can pull it back. So you can pull back homological information on this side to information about C. So this was the point of Klein partial, one of the points there were. Okay. But all that stuff goes on in characteristic P, and I'm still working in characteristic 0. Okay? And then another useful thing about this approach is one can also use the notions of Donkin, for instance, to construct. So Donkin has these notions of good filtrations of modules, wild filtrations, so by standard modules. And then you can, together with these, you can construct tilting modules. So you can construct lots of interesting examples of modules with this kind of setup. And since one doesn't know very much about representations of these loop algebras, these will all be mechanisms, if one can play this game, to produce lots of examples. So this is my goal. And since I have an algebra which is really doesn't fit into either of these models, I have to keep tweaking it so that I can get to a situation where I can sort of prove results which are similar to them. So the motivation for sort of all these various reductions that I can do quantum affine algebras, but that's another story. So, okay. So the question now is how to make this work, how to do some of these things. For finite dimensional representations of loop algebras. Oh yeah, everything's over C. That's bad enough. So the first thing is that this category is too small. You're not going to have enough projectives or injectives, okay, inside this category. So you have to somehow work in a bigger setup to get any information. So so we work in a bigger category, which is sometimes called I. So I'm going to keep changing. But I is going to be the category of LG modules which are G locally finite dimensional. Yeah, I'm going to allow infinite dimensional modules, exactly. So in this category, I immediately have enough projectives. So if I take any lambda and p plus, if I take lambda to be dominant integral, and I take v lambda to be the corresponding irreducible representation, which is finite dimensional, okay, then I have a projective module, standard construction. You just induce up from the finite dimensional module. And since you're working in a so you're looking at relative, since this is semi-simple as G modules, it becomes automatically a projective module in my category. Okay. And then, so then there's another device which is quite common. So which is, supposing I have another, so if I take another dominant, so let's define a partial order on P plus, the usual partial order. So this is less than or equal to, and you say that mu is less than or equal to lambda if lambda minus mu is in the non-negative span of the positive roots. So it's in the positive root lattice. So given any object in my category I can define the truncation at some weight lambda, for instance, to be V modulo the submodule generated by everything of weight not less than or equal to lambda. I should say that this category, in this category, once you insist that they're G locally finite dimensional, anything continues to be a direct sum of eigenspaces. Right? So I just do this truncation. And now I can define the analog of my Verma module, which in this context is called the global Weil module. And this is exactly like the Verma module is defined. For instance, you take the projective and you truncate. So Weil module is you take p lambda and you truncate at lambda. You get rid of all weights which are not smaller than lambda. But so far so good. And so here are various issues. This W lambda is infinite dimensional. Okay? And then that's a problem. And the other problem in talking about Jordan-Holder series, then you have a problem. And the other problem also is that my category I has far too many irreducibles. So my indexing set of simples is not very nice, right? In the case of category O, or in the case of the algebraic groups thing, you had some nice discrete set which indexed it. Whereas here, what are the irreducibles? If you remember, we started off by saying that the irreducibles all look like this. So you have these very continuous parameters showing up. So my poset is somewhat unwieldy. I mean, I don't even know how to make this into a poset to begin with, because these AIs are non-zero complex numbers. Okay. So we change our rules yet again. And I mean, so the question always is, why do you change rules and why is it a reasonable thing to do? And for that, the motivation always came from somewhere else. What I'm going to do now is instead of looking, so supposing I have V as a finite dimensional module for LG. Okay, so what does that mean? That means that you have this map from here to here, and the kernel of rho is finite dimensional, is a finite codimension, right? And then kernel of rho is an ideal, and it looks like G, and any ideal in LG looks like this, modulo an ideal I. So it's in fact comes from an ideal in my Laurent polynomial ring. And then this is just isomorphic, of course, to G tensor CT. Since you're in a PID, you can just do that. I intersect CT. So I'm going to stop thinking about representations of the loop algebra, and I'm going to start thinking of representations of G tensor CT, which means I'm thinking of representations of the parabolic subalgebra in my affine algebra. Okay? So, and of course that plenty of people have studied. That's what de Mesure modules are all about in the context of Kac-Moody algebra. So we're going to replace, so then it becomes okay to replace LG by G tensor CT, which is the parabolic, maximal parabolic in G hat, in my affine algebra. Okay. And my category I, so I want to get into a finite thing. So G tensor CT is a graded algebra. Z plus graded algebra. So if you remember, I mean, the usual definition of the affine has a derivation, but here you can just think of it as powers of t. Okay? So here's my final modification. So this is going to be my category G, which is the category of graded GT modules. So of course, Z graded GT modules. That means that V is going, any object here, V was going to look like a direct sum of VR with R and Z. And I'm going to make my life simple and assume that it has finite dimensional graded pieces. Okay? So what are modules that live, what are well-known modules that live in G? It's basic, so I think here it would be, the natural example would be that they are the de Mesure modules in the positive level representations of affine Lie algebras. Okay? And in fact, those, so. I'm going to write it. Okay, okay. So I'll tell you in a minute. So these are, so the de Mesure modules in the positive level representations live in this category. So I'll explain these words in a minute. Of G hat, R in G. Okay, de Mesure modules are the following. So let me tell you what it is for a finite dimensional algebra. You take V lambda, yeah? You take an element of the while group, okay, W and W. Then you know that dimension V lambda, W lambda is 1. You take any non-zero vector in that, okay, and then you take UB of that. Or you can replace B by the parabolic. So I actually mean the parabolic here. Okay. So let's see, what else? Positive level, that means the center acts non-trivially on my representations. Positively on my, as a positive integer on my representation of the Kac-Moody algebra. Okay, so there are natural examples which live in this category. So what is the advantage of having done all this? So we have G, and of course so G is graded GT modules, okay? Z graded GT modules. So why did I insist also on changing from GT from LG to GT? After all, GGT inverse is also graded. It's for the following reason. Supposing I take V in objects of G, and I ask, when can V be irreducible? Yeah? So I have V equal to direct sum VR. So V is irreducible if and only if it lives entirely in one space. So if and only if V is equal to VR for some R, in which case V must be isomorphic to an irreducible G module, which is V lambda. Right? This is because supposing you have VR is different from 0, then everything bigger generates a submodule because I'm only working with GT. The grade keeps going up. Right? And so I have a submodule, and so I can get rid of it. If I worked with GTT inverse, then that would go up as well, and I'd be in a mess. So that's why I prefer to do this. Okay? And as far as understanding homological properties, we agreed that it didn't matter. So once I do this, what have I got then? So then I've got my poset is now at least nicely indexed. So poset, well, it's as yet not a poset, but the indexing set of the simples well, what do I need to tell you what a simple module is? I need to tell you what simple module of G I'm taking and what grade I'm making it live in. So it's indexed by P plus cross Z. So I want to tell you, so how do I get a simple object over here? I've just said it has to live in a particular grade, right? That picks up the integer. And it has to be irreducible as a G module when it lives in that grade. And irreducible modules are given by dominant integral weights, so it's P plus cross C. Okay, so now it's become a discrete data. Yeah. Yeah, I'm integrable. I said dimension VR is finite. Okay. Actually, the de Mesure modules in level 1 will play a big role in this thing as we go along. Okay, so now, so given any lambda r in P plus cross Z, I'm now ready to start defining my triumvirate of modules. The first one is this V lambda r, okay, which is the irreducible module associated to lambda living in level R, grade R. Let me tell you how to define the global while and the projective. Okay. So how did we define the projective? We defined the projective originally in this way. Right? Now GT is a Z plus graded algebra, so the universal enveloping algebra acquires a Z plus grading. When you take a monomial, you just add up the powers of t. So you get a grading over there. So this is naturally a graded module. So I'll just declare this to be my module P lambda 0 when I think of it as a graded module, and then I'll do degree shift to get P lambda r. I'll just lift all the grades up by r. So P lambda r is defined. Okay? And W lambda r is also will be defined in the same way. So how did we define W lambda r? What did I have to do for that? I have to take P lambda r and I have to go modulo all weight spaces in P lambda r, which are not less than or equal to lambda. Yeah? All I have to tell you, to make sure that it remains graded, I just have to tell you that this is a graded submodule, but that is clear. So this is a graded submodule, so I quotient, so I've got my global while module. Okay? And so now life is getting better. But I still haven't got out of this annoying problem that P lambda r is finite. So W lambda r is still infinite dimensional. Okay. So this causes us a little bit of difficulty in formulating the result. But so the first part, let me state the first part of the theorem. So P lambda r has a filtration so it's what you would expect, P1, P2, and so on, such that the successive quotients are global while modules. Mu I Si. So all the work now is my joint work with my students, Bennett and Manning. Okay, so I have this, and to complete my result, I should really tell you something about what kinds of things appear. Yeah.
This filtration is not finite or will not be.
This has an infinite filtration, such that the infinite filtration, and to get information about characters, the intersection of all pk's will be 0. So that you don't have anything, you don't lose anything when you're doing this. Yes? These terms. Okay. So remember, I'm calling these modules W lambda r, and they're called global while modules. And I've been making a fuss about de Mesure modules, which are finite dimensional. So I have to have a way to go to the finite dimensional case, and those are called the local Weil modules. Okay, which I'll write as W loc lambda r. Okay, and what these are finite dimensional quotients of this.
These are de Mesure modules?
These will, in some cases, these are de Mesure. Yeah. For algebras of type AB, no, for algebras of type ADE, these are de Mesure modules in level 1 representations. This is a different present, I mean, these are defined differently, and you have to do a fair amount of work to show that they are the same. So these are maximal finite dimensional quotients of this. And the reason these are called Weil modules, I mean, the reason we called these Weil modules initially was because they are the q equal to 1 limit of representations of the quantum affine algebra. At the quantum affine algebra level, they're irreducible. Here, they're indecomposable. So that's the analogy with characteristic P again. So these, yeah. So how are these defined? You just introduce one additional relation. So you, let me not say what they are, since I never told you what the relations are that. So you introduce one additional relation. For algebras of type ADE, it's a theorem. So due to, in the AN case, it was proved by myself and Loktev, and then for the arbitrary ADE case, well, originally there was this work with Presley, and for the arbitrary ADE case, Fourier and Littleman used the result for SL2 to do it for all ADE, but they still needed the SL2 result. That local Weil modules are de Mesure modules. In the basic representation of these algebras. And in the general case, it was proved recently that the local Weil modules have a filtration by de Mesure modules, and non-simply laced case, so you can compute those things. Okay, so to complete the theorem now, so I've got these local Weil modules. These are finite dimensional, so they have Jordan-Holder series. Okay. So the second part of the theorem then says that if you look at P lambda r and you ask yourself how often a particular global Weil module appears in it, okay, then that's equal to the multiplicity in the local Weil module, so mu r doesn't change, of the irreducible module V lambda s. Yeah. This is the irreducible G module with the dominant integral weight lambda.
And what is the parameter
S is the grade, which grade it lives in. Right, we're working in a graded category, so you have to put it in the appropriate slot. Okay. So this is the BGG reciprocity. And actually this is more like, as I said earlier, this is more like a Brouwer-Humphreys reciprocity. Because if you're playing, and I should say we only did it for SL2, it's not done for other algebras. But it's going to be correct. So for SLN plus 1, I think we know how to do it, but for G, general G. So this is actually more like Brouwer-Humphreys reciprocity. You can think of these as standard modules. So let me write, you can take duals, and then you have injectives. If you take the dual of this, then that's the co-standard. And then this looks like the standard. And this is the irreducible, which I think is what Donkin calls the Brouwer-Humphreys reciprocity. So this is analogous to that theorem. So this is the first step in proving this kind of highest weight categories thing in general for arbitrary G. But SL2 has taken long enough, so I will stop now. Thank you very much. Approach to this as well. At least to these local Weil modules.
But for the global Weil modules, no geometric interpretation.
Well, there is a certain amount, yeah, I don't know a geometric interpretation of it, but the point is, So these global wide modules are somehow also right modules for a polynomial algebra. Okay? And right modules. And the local wide, so that's why the local wide modules are then just obtained by tensoring this A lambda with a maximal ID. And so the result is that somehow this is free as a module. This is free as a module for this polynomial ring, if you're working with CT. Now you can replace CT with an arbitrary associative commutative algebra and play this game. In which case you can still define all these modules, but the structure of this local module depends on what point you pick over here. The dimension and so on varies. So again, there is some geometry which will come from analyzing this ring and what variety it finds.
You have given reference.
Yeah.
So your definition of this zero module, that P which you
Yeah,
that's GT.
that's right.
That's just going to GT.
Yeah. Because you're working with level 1, it's okay to do that.
What do you mean by level one?
The center of Cassellati algebra acts as what? So it's the basic, what other basic process.
And you also notion of level 1 module for denominator modules also? No.
It's a de Mesure module in a
Oh,
level
can
1
you-
representation of the affine.
Oh,
Right.
And this other thing you mentioned about non-simply raised cases, there being filtration by using one. So what's the reference for?
That is, that's on the archives. The name is K now V. And it is recent in the last few months. Yeah, so I mean, so he tells you what the graded multiplicities are. So it has some connections with this Kashiwara's crystal basis, and there are some combinatorial functions associated with it.